So let's get started. Just a reminder that we usually reply to take your attendance and participation. And today the goal is to finish the probability chapter. If not today, then will be Friday. So homework will be released. I think we'll give you 10 days to do it. Or I don't know, tomorrow other section. I mean, we are a little bit behind for that one. So probably if uh, I release the homework either on Friday or next Monday, because to make sure that the two parallel section have the same time, start the same time and end the same time. So if not Friday, you will know. I mean, but we'll be sure we should able to finish this week for our class. So so let's continue probability. I guess we cover up to conditional probability and multiplication rule. So that will then we'll finish the rest of that. The Just to remind you what we have done. I mean, last Friday is from the probability that we learned from the classical version, which is Laurent frequencies. The ratio is a fraction where you take the number of outcome favorable event over the total experiment you run. So the idea is empirical idea. You have to run some experiment, and the experiment can be repeated, and the uncertainty thing is going to be stable, so that you can do this experiment, right? So the idea is this have to be done repeatedly, and then this thing doesn't change, right? If things change over time, then this doesn't work. So it seems like this apply to many cases, but a lot of case business world doesn't fit very well, right? I don't think you would say what happened last year would apply perfectly this year, right? Or some even in the physics world, right? And then there's some difference in several dimensions, like the weather forecast, right? It doesn't apply to this. So we need a more robust definition of probability without relying on something we call, is it maybe not working very well? So let me put the mic a little bit higher. Rely on the idea doesn't work. Let me see. Is it working? Working? No. Hi, hi, hi. It's weird. Okay. Hi, hi. Whatever. Okay, maybe I use this one. Um, just to remind you that you really need to extend this beyond what is here. Have to be like consider case where you don't rely on experiment. So the idea is if you don't use that, then you have to uh use some math, right? So because you have to rely on something, right? Because you can't be out from nowhere. So we really need to have something, and then that rely on math. And the math rely on the probability actually require you to have three axioms, which I repeat now is for the probability you require to talk about is now is no longer a number that based on the real world, right? Because in the real world, we do a lot of experiment, you just do counting. But now you don't have counting, so you have to define it as a math thing. It's a function which you give me the event, I give you a number, okay? And the number must be between 0 to 1. And probably you would say this is trivial, but do remind yourself that odd ratio that we studied last Friday is also representing likelihood of certain thing, but that is not from 0 to 1, which is from 0 to infinity. So 0 to 1 is not a trivial thing. Okay. And second one is saying that sample space is 1. So it does mean something, means that we do know what are the possible outcomes. And I do remind you that it's not magic, which means that I put my hand in the urn, doesn't come up with a rabbit. Okay, so that is the second thing. And the third thing is, I think this the most bite is on this one is, if you have a event that consists of mutual outcome, then probably the event is the sum of probably the all outcome. So the probability of the whole is sum of is parks. Okay, as long as the parks are not overlapping, right? So basically, just like the classical idea where you in the kindergarten, right, just try to color the whole area, but you color all at once, the same as you color parks one by one, right? So that is the main thing. And then turn out this is a very important. And if you learn math, you know this is very natural when n is finite, but n is infinite, which we will need it when we talk about numbers. That would be the most bite is on there, and that one is non-trivial. And because this is something very normal with the problem, you would say, right? Whole is sum of its park, but when you have infinite many parks, then mathematics will tell us there are a lot of issue there. But of course, we're not mathematicians, so there's not something that too much worry about. And this illustrate to remind you why this would allow us to go from probability that without running experiment. Just to quickly go over that again is from this from this sample space, we know the whole space is 1, and we know this can be decomposed into different number here, okay? So the key part is this one, okay? The die is fair, okay, for this calculation. And this comes from what? This doesn't come from experiment. This comes from our engineer understanding. If we create a die fair, which means that every side is perfect, if we create a die is fair, in that case, we will expect from our physics, right, this each outcome is equally likely. Then end up in each number the same, right? Just that means you solve this equation, right? This is 1, and this is 1, right? This all are x are the same, right? So you solve 6x is equal to 1, so x is 1 6. But this comes from the engineering idea with our knowledge from physics, or that would give us 1 6. Of course, you may say, okay, I don't really need that. I just say, okay, I from the data, which is actually each outcome is equally likely, right? We don't really use physics, but we just have enough large number experiment, and each outcome is equally likely, then you also get the same result. But we have additional thing is we don't rely on real world. We can rely on engineering, right? But that's equally likely. But of course, you can say, okay, now we are producing an unfair die, which one is more likely than others. Say, suppose one is twice likely as all the other number, then you change x to 2x, right? In that case, x is 1 7, right? And probably the one is 2 over 7, the rest is 1 7, right? So it really depends on the can depend on engineering thing or depend on data, right? Data shows us that one is appear twice more time than other numbers. So from this one, now we relax ourselves from one experiment, right? And if we believe the data in the past apply to the future, this would apply equally well without talking about random experiment. Okay, we can rely on extend our knowledge from the past or our knowledge from science, engineering, okay, or a business knowledge that would change, right? Say, for example, you think that the future is more likely based on your business judgment, then you can also change this number as well. So I hope that this gives us why we need to learn the axiomatic definition of probabilities, because of we want to use data or knowledge to make our probability calculation. Okay. And other things that continue is there are several rules that we learn about probability, and you may ask why we learn these rules. One main reason is because of now we rely on data or rely on knowledge, right? We don't repeat everything out, right? But there will be some probability we can't really calculate directly or we estimate directly, right, from the data, right? Then we need to rely on this rule to do our calculations, right? And this calculation have to make sense. Right? For example, the example we said here is, I'm not going to repeat it, but we have done it. It's like roll a die, right? We want to know the probability that you get less than 6, right? But probably from your data, from your judgment, from your engineering the production of the die, you only know 6, right? Have 1/6 of chance coming out, right? You have no idea about 1 up to 5. Maybe the die is unfair. You don't know how likely is 1 to 5, right? Then in that case, you have to use this kind of formula to calculate, to generate that, right? Or the idea is you only know one thing. These rules will generalize to all possible other event that you do not data on. Okay, so you don't have to, like random experiment, you should run all many times to know everything, right? But you can extend your knowledge based on that, right? So same as the other rule there, right? Is all the addition rule, right? And your knowledge may tell you the probably A and B or intersect B, but you don't have a union, right? So we allow us to calculate by this formula, and this formula addition rule is just simply the idea of filling color, right? The red circle plus the purple circle minus the overlapping pink is the goggle shape, right? So that is something you will not be surprised when you learn from your kindergarten, right? And this is total probability rule, is also very intuitive, right? Is A is equal to A and B, and A have no B, right? That is the idea that this diagram, right? The red circle, right, can be decomposed in 2 parts, right? Maybe it's color. This is part 1. It's the black one, right? It's A without B, right? And the other is, let me see what color I should use. Green, maybe green, right? And the other one is the thing with B, right? So that would be the 2 things that we would be talking about, right? A, the red circle, is the black plus green, right? Must be, right? It's by either A with B and A without B, right? So all these are super useful to do all the calculation. And then last class we talk about odd ratio, and as I want to remind you, odd ratio is probably the earliest way human would try to quantify futures, and it runs from 0 to infinity, and that infinity is not very convenient to say because what's infinity, right? So it's not in numbers, it's hard to say. So that's why we narrow down the range to 0 to 1, right? Just you may ask, okay, actually you have seen this kind of normalization before, right? Covariance and correlation, right? Covariance is negative infinity to positive infinity, but correlation coefficient from -1 to 1, right? So normalization is very useful because we know 1 is perfectly up a sloping line, -1 down sloping line. So same as here, 1 is almost sure it happened, right? 0 is almost sure it doesn't happen at all, right? So it's very clear what's going on there. And again, odd ratio is still very useful because we still see it in the gambling and betting industry, right? And we want to mention last class is betting, right? The odds can be converted back to probability, right? By solving the equation, which you can just reverse this one, right? And in that case, we can figure out the probability from the betting odds in the casino, right? So when someone asks you, okay, how likely a soccer team would win in the upcoming match, if you do not watch sock away often, you have no idea, right? Maybe you say half and half, right? But if you want to have educated guess from this class, right, then go to the internet and look at the gamble betting and do the odd ratio, and you have some idea which team is going to more likely to win, right? So that would be the thing, or any other thing is like the poly market, right? Most of the thing can be bet there, then you can go there and check out, right? The ratio who is more likely to win and who to lose, and that would be the idea. So after that, I think here comes I guess it's the most complicated thing, I would say, probably in this class, or even in this course, is to understand how you should update your probability, okay? And if you say, okay, why it matters? Because probability is how we view our world, right? And that is how we learn. And indeed, that is as I also said many times, this is the basis of machine learning, right? I mean, this is probably, if you take this way further, and how machine can learn is basically from this one. So before we go, and then we talk about the conditional probability here, is the definition is given B, right, is if B, B has happened, or you think B is going to be true, and how likely A is going to be, right? And that is going to shrink your sample space, right? Because now only B is relevant, okay? So that means that only B is relevant. So only relevant part is this guy, right? You consider A and B is the only thing relevant, right? But now, because of the probability has to satisfy axiom 2, right? Which means that give you the whole sample space must be 1, right? So you divide the probability B, right? Because if A is equal to B, it must be 1, right? Given B, the probability B must be 1. So you have to divide that to get it there, okay? But I'm not going to prove it. If you look at all the introductory text, this is given by definition, not proof. But if you go advanced math class or stat class, you prove it out. So because we're in elementary, right? So just take it as given. But you can actually prove this guy to be true. But in theory, it's not something terribly difficult, right? Because give example, right, like this, right? If you have even number, large number, right? Given no even numbers occur, so the even number strength from 2, 4, 6 to 4 and 6, then you can calculate the same thing there, right? So that would be the same idea as you do this ratio calculation. Okay, I'm not going to repeat that. If you have any question, you can try to look at it again. And as I said, there will be assignment either on Friday or next Monday. Then you work on the assignment, then you learn. Okay. So basically, just like this question is like, going to be true, large it comes out. How like is even? So now the sample space sinks to 1 up to 6, but now it's 4, 5, and 6, and even is only 4 and 6. Okay. So that would be the main idea behind. Okay. So at very last, we stop at this one. Okay. And this one, the rule of this guy is just nothing a deep thing, but just you multiply probably B on the both sides, right? Just give you the first equation. And the first equation is come from that definition. And A and B has no particular meaning, can swap between A and B, so you get the second line, right? So that is nothing very deep there. You call B and A and B the same thing, okay? So here give you the example that why this is convenient, right? Because sometimes we do things sequentially, and this conditional probability gives you a handy calculation. Otherwise, you have to calculate 30 possible outcomes, and you can count how many of them, but that make our life easier. And many of you in the high school, right, have seen this calculation, and then will tell me, okay, you didn't learn this way, but rather you learned this tree diagram. Okay, maybe I would just go slow on this tree diagram because this is something that we'll be using more when we talk about Bayes' theorem, which is the most important thing, okay, in this class, or at least for the first half of our course as well. So here we have urn containing 3 white and 3 black. Okay, 3 white and 3 black. Okay, and depends on the first draw. The first draw is either black or white. Okay, If you draw the black one, you end up one black less because that's gone because without replacement. If you draw white, because then will become 3 white and 3 black. Okay. Once you do that, you can do the calculation again because you are close to eye and draw, right? So the second one is black, will be 2 out of 5. If white is 3 out of 5. Okay. And similarly, below you have the same idea. If you have 2 white and 3 black, then the black will be 3 out of 5 and white will be 2 out of 5. I hope this is clear. So now the question will be asking actually, you would have 4 types of outcome, right? Either the first 2 ball are black, right? Or you have black and white and black, and white and white, right? Then you can want to know the probability of each outcome. And then black and black, right? If you follow the multiplication rule, right? This is the probability B1, right? Probability B1. And what's this probability? This probability, if you remember the example, this is B2 after B1, right? So multiplication rules tell us that if you multiply along the branches, you give you the end of the result, right? So multiply 1/2 to 2/5 give you 1/5 is the probability of each edge. Okay, so just multiply along the way. Okay, multiply along the way, give you the outcome you want. Okay, no matter how long the edge is, it's always like this because multiply along it. Okay, because that is the probability rule, right? Although we just tell you the multiplication rule for 1 level 2 level 3. If you have more tree, the same thing. Okay, it's just multiply along the way. But of course, our class limit ourselves to 2. But this rule apply to any other thing. Okay. And similarly, you ask what happened. The probability is you have first black and second white. Same idea. Just multiply this according to this. Why? Because 3, 5, okay, is probability of white of 2 given black 1, right? So you multiply by probably black one is this. Okay, so it's 3 over 5, 3 over 10. And similarly, you can do the rest. Okay, I'm not going to tell you one by one because this is too trivial. And you also learned in your high school if you have learned before. Okay, but that is the idea. You will see add up to 1, right? This 4 number add up to 1, right? Because you either have 2 black and white, white and black, and white and white, right? So you only have 4 possible outcomes. Okay, and that will give a tree. Very soon we'll just use this tree again to get our most important thing, Bayes theorem. Okay, but I hope so far that's clear what's going on. Okay. And here is the rule, which will be super useful. Is remember the total probability rule is A with B and A without B. Okay, and and here A and B can be again use the multiplication rule, divide A given B times B. Okay, and here with another one, A and without B will be A with given without B and times probably B. Okay? So that's nothing but just applying combine 2 rules, and then you ask, okay, why we want to do that? Okay, very soon we will be using this formula, but that is nothing new but applying what we know. Okay, but let's look at this example. I think that is the very useful one. Okay, so you have seen there's a 2 bets here, A and B. Okay, and A have 4 white and 1 green, and then another bet is 1 white and 1 green. So basically, you just have this. You have A. Okay, you have 4 white and 1 green, and you have B here, which is 1 white and 1 green. Okay. Okay. The question is asking if you choose a board bet at random, you close your eye and choose either A or B, and then you draw one ball there, okay? How likely that is a white ball? Okay. Is that clear? So probably you ask, okay, why I ask this crazy question, right? Who is going to care about drawing balls for me? Bad and then this, okay? Let me tell application. That's very simple. A is e-commerce good. B, e-commerce bad. A with white is the stock goes up. Green is the stock goes down. Okay. E-commerce good, more likely the stock goes up than go down. E-commerce bad, it's random, right? Can be good or bad, right? So the nature decide, not I choose a bad, the nature decide whether it's good or bad economy, right? And then if good economy, then something comes out. Okay. So if I ask how likely is white ball, it's asking how likely the stocks goes up, right? Which we care, right? And why we care about this? Because it's very difficult to analyze whether the stock goes up, right? But we can easily say if e-commerce is good, what happened whether the stock goes up or go down? If it's bad, goes or go down, right? So divide and conquer. You divide things into different scenario and do analysis, right? The scenario analysis, and you combine different scenario, okay, through this rule. So this is something you would do very naturally, right? So I hope this convinces you why we need to do this, right? Why we care about drawing balls from an urn and then pick up which bed is there, right? It's completely crazy. But it's what you do in investment, right? Or what you do in business, right? And maybe A is application, say A is a good weather, B is bad weather. You're doing restaurant, right? If weather is good, right? More customer comes in, which is a white scenario. If green would be best scenario where we few customer. Want to know whether today we have a lot of customer and very few customer. Okay, there's something like this. There's often like this happen to be here. Okay, so there's nothing something too crazy. Okay. So let's go back to the question. I want to know how likely we have the white color ball. Okay. And how we're going to do that is looking in the world where A is being chosen and the world without A, right? Which is B, right? Because either you're A and B. So white under A or white under B. Because it's a divide and conquer idea, right? And white under A can be decomposed into what we learned just now is the multiplication rule. Okay. You go to A and times the white under A. Okay. And A is equally likely. Okay. In this case, because I chose at random, but you can, if you talk about economy, right? Whether the economy is going good or bad, can not have to be 1/2, but in our case 1/2, but you can change to the number that what you think. Okay. And this is because you have 5 ball here, 4 of them is white, is 4 5. Naturally, then you're done the first one. Okay. You know how like you get a white under A, right? And similarly, you can do the same idea. You have Y under B, right? And use the multiplication rule. You divide it in 2 parts, right? B, right, under B, okay, and then you have the white, okay. Under B is 1/2, and you because 1 white and 1 green is 1/2, okay. Then multiply is 1/4. Add together, you give white is more likely, but it's not too much more likely, right? Because without calculation, you think okay, you have 4 whites compared to 1 green, right? You would think that white are very likely, but you have to discount the fact that you may not draw bad A a lot of time. Okay? Even though someone tell you that, oh, when income is good, the stock is going to go up, right? They need to be very careful how likely that recession is going to be there, right? Even it's equally likely that is white and green, right? In the case. So it's not that much, right? You would think it's more than 65%, right? Right? Because you have 4 white ball after green ball, right? Yes. But it's not too much different from 0.5, slightly more than that, but be very careful. So that's why calculation has to be there, right? Because you would think that, right, from this question, you would be tempted to think, oh, it's very likely to have a white ball, right? Then you should be have like maybe 7%, 80%, or 90% even, right? But you have to be very careful. Have discount the fact that how likely that the nice environment going to come out, right? Then that is something very important. Okay. And to understand this I think I have the tree table. So the first thing is whether you have A and B, right? In this case, at random, it's 1/2, but this number can be anything if you like, depends on scenario. And then after that, we look at A scenario and B scenario. A scenario, white is more likely than green because it's out of 5 balls, 4 are white. Okay. And in below, we have back green is equally likely as white and green. And as I told you, you just multiply along the edges, give you the final answer, right? So that's 1/2 times 4/5, it gives you the final answer. So you get the 4 possible scenario by multiplying the edge. Okay. And the last question is asking how likely is the white, right? So that is using the addition rule, right? Whites only have this and this. You just add these two together, right? Add this together, get your final answer, right? So that would be the idea, right? So you multiply on the edge, okay? And you look at what the outcome favorable to event, right? Just add together, right? So that is how you use the tree diagram to do the calculation. And then you have seen, if you do the high school, you have seen this before, okay? Or if you forget, it's okay. Just remind you to get there. Is there any question? Then a question? If no, then we talk about independence. Okay. Once we did that, then we are ready to do the Bayes theorem. Okay. And this is one of the most trickier part of this class as well. Is what is independence? Independence in probability or statistics means telling you the information doesn't change your probability. Okay? You didn't learn anything new. Okay. The idea is the following, and the 3 of them are equivalent. So any of them will be fine. Okay. If I tell you B doesn't change to A, same as before, independent. Or I tell you A doesn't change your B, is independent. Or the intercept is just multiply, is independent. Okay. So that's the definition. Why? What is the meaning of that? Means that the independent means that, say, suppose I toss a coin and roll a die. Okay. And I would say most likely they're independent, right? I'm telling you that the die is even number. Does any change your judgment on the coin, whether it's a head or tail? Probably not, right? So it doesn't have to be related. Okay. But if you tell me your morning is eating McDonald's, right? Then probably your dinner with McDonald's will be different, right? Maybe more likely or less likely, but probably not the same, right? So that is dependent. Okay. And for example, you look at this example. If I have this give you this A, B, and A and B, then you can check whether independent. It's very simple. It's multiply them. Is it going to be the same as the intercept? If not, then it's not independent. Okay. So it's easy to check because by construction, just checking this, you know it's independent or not. Okay. But to test your mind, okay, see the following question. If I draw a ball from an urn, okay, from a pot, from an urn, and then I draw it, okay, and put it back, okay, I draw it again, then the first 2 draws are independent, right? Because what I draw in the first round, I put it back, the same balls is there. So the same thing happened, so independent. But if I draw the ball and don't put it back, I draw a second ball, then they're dependent. Okay. And to make you more fun, okay, let's look at what we learned before, what we call mutual exclusive. Okay. And by construction, mutual exclusive are dependent. Okay. Repeat. Mutual exclusive are not independent. Why? Because you know one is going to be true, the other one must be false. So it gives you some information. Okay. And of course, exhaustive is also not independent, right? Because you know one is false, the other one will be true, right? So I tell you something about that, it can be, right? So just like go to the courtroom, right? Independent means telling you this information is irrelevant, right? But if relevant, right, no matter how small it is, right, that will be independence will be dropped. So it's a very strong concept, independence. And probably you ask why we need to do that. Okay. Actually, we are assuming all this when we collect data. Later you see. We want that each observation from our data, by assumption, is independent. Okay. If data is dependent, then the power of the sample will be very little. Right? Suppose the data collect from the first one is highly correlated with the second one, and all the data will not be very useful, right? Because you only have one observation, right? Right? It's not more meaningful, and that's what we assume for the when we do the second half of course. We will make the assumption that the data we collect and each observation is independent. Okay, and in that case, each observation will be meaningful, will be very useful. Okay, and that is something we hope to get, but of course, in the real world, I mean, there's things are related in some sense, right? We learned what we call the butterfly theorem, right? Something somewhere down in the Pacific Ocean, a butterfly flip its wing and going to probably cause a typhoon in Philippines, right? So what things can happen, but let's assume for many cases, we assume independent, right? So if you try to randomly draw a sample, collect sample, then you hope that it's going to be independent, right? Otherwise, things will be more complicated. And that's why when you learn financial data, the prices are not independent, right? Price of today is related to what happened in the past, right? Or price movement at this very minute actually related to what happened in the very last minute. So when you talk about financial data, actually, we rely on we have a problem of data related. So that's why you need to learn financial time series. We need a specialized tool to handle financial data. Okay, but that's beyond the topic of class. So that's why we assume in throughout the course we assume independence. Okay. And that's why when you try to apply a project to financial data, have to be very careful. Okay. And uh, and that's why when we do marketing survey, right, we're not trying to ask the same person over and over again, right? If we ask you, I don't ask your family, right? Because high likely that you and your family will be very similar. So we try to do a survey based on picking different people, try to talk to many people, right? Otherwise, the data is not represented enough to be useful. Okay, I hope that explain why we need that. But don't worry about that. I mean, these are black thing. You are not expected to know for your exam. Okay, even if you need it, you are open book, so you can bring your notes there. So before break, I want to introduce this formula. I will leave the detail after the break, but this is so important. I want to introduce this and talk about this after break as well. So what we are doing, so basically this is almost like the crown of the probability theory, which is the most important rule. So you can see the left-hand side is nothing, but I tell you B was A, okay? And this is this guy, okay? And if you remember the formula of conditional probability, right? So that is the probability B, right? And the numerator is just A and B, right? If you remember that. Okay, if you remember the formula. Okay. and you just rewrite the numerator by multiplication rule, right? So you be asked, okay, why you call it base rule? I mean, nothing new there, right? Which is just your definition of condensation probability, and you write the numerator by multiplication rule, right? Why it deserve a name called Bayes theorem, right? Completely no sense, right? You ask, okay, why we did that, right? But do you know what happens here? Okay, as I said, we say this is learning. We're learning. Initially, we have an idea how A is likely to happen. Okay. Now, this is what happened initially. This is our initial thing. Now we know B has there. B may be evidence. Then we want to know how likely A under the evidence B. Go. We learn more. Okay. And this is how you update is to multiply by this guy. Where's my pen? So this guy is updating factor. So from probably A, now you know B happened, you multiply by something, which we will tell you later why this is true. But I mean, of course, you know this is true just by definition, but we tell you a little bit more why this is true, intuitive sense, right? And you become this one, okay? From right to left-hand side, okay? From what you know, it's probably A, and you know B is happened. So we want to know A again. Okay? So that is the idea. Okay? And probably just I give you some use case first, right? Maybe A is the probability that the stock is going to be $100, right? Well, the stock is going to be very good. Okay, say for example. Okay. And now you see the evidence B, maybe B coming from say Tesla is going to be $1,000 in 5 years later, say. Okay. And you see B maybe evidence of, say, they have the self-driving is going to be going well, or you have some evidence that many people using the robot taxi, or many things you can say evidence, right? And this evidence can help us to improve our prediction whether the stock is going to go up. Okay, so that would be the application, right? Or in the court case, A is how likely the guy is guilty of the murder. Okay, and B is, well, he expressed some hate speech in the past, or he has a quarrel with that guy last night. Okay, or maybe B is actually he accused of murder, but actually this guy is maybe in the other parts of town. Okay, or actually in another town, right? He's killed in town A, but actually he's town B, right? And in that case, right, if he actually murder, but actually it's town B, then probably this is not possible, right? Then this is from 0, then he will not be a murderer, right? So that's what happened, right? If you learn that he's not actually in that town, how can he kill the guy, right? So that would be thing, right? Or if it's more likely that he is actually fight with that guy, right? Or they have some financial conflict between them, right? Then this goes up, right? And how we revise this is based on this formula. Okay, so that would be the idea behind. Okay, so I overrun by 2 minutes, but we'll go to this again. But just to remind you, what we're doing is from A, you know the knowledge of B. Okay, we update our A. Okay, so that would be the key. We'll give example and explanation for this one. So don't worry about that. We'll do it after the break. So I said in the meantime, we will do the you will apply as the way to see your participation and attendance. So please fill that in. This time, from now on, we require you to sign in your CUID. Okay. There's a break of we go over about 3 minutes, so we resume at 11:38. Just to remind you, please fill in because it's part of your participation points.
張三合。B.B.A 咁多，嗰度講就係張多啲人定四多啲啊？四係三，你哋幾多啊？Like she didn't even try to it, and I said, "How is it?" Another one she said. 我哋嗰度冇考慮啊，好少做好多香港嘅嗰個大語我數多可能好少年，我小朋友都夜晚扎醒嘅，發咗。已經俾佢有啲趣味啲嘅，呢個係網絡嘅，一條友打嘅，一條打，跟住都興嗰啲一齊打嘅，我 friend 啊嘛，宿舍嗰陣時真係食一度咁。前條咧打機到一路揀 IP 嘅，而家揀好多啦，本身就係勁嘅喎，有個 server 都係喺度內聯，你而家係話我打嗰陣少咯，我今日機打佢都唔太老啦，差咗一腦。有咩好玩？我 part time 嗰個發係有個學生就喺騰訊做，佢問我有咩遊戲可以玩，佢做遊戲。老師有咩遊戲？俾你幾個遊戲玩啊？我都唔玩遊戲，我玩 我都唔玩。我 skill 就係個思維嘅嘢嘛，你學咗開始就創作思維，開始你覺得係咩？即係你去相親，相睇嗰陣時，你覺得啊個女飛個男個女非常之好，見完之後覺得仲好，一個好啊，跟住個男嘅一邊差。可以變差，可以變差，可以變差。 譬如話好勤快嘅化妝術咁樣，或者你係我成日我轉到邊個嚟？因為你一班 B 發生咗啦嘛，佢對上班先可以跌翻一㗎嘛。即好似我哋開始講嘅雙貨幣形式係呢個係 B 嗰陣，呢個就係每個 B 嗰陣就係一個，咁所以叫做其實 B 嚟嘅。因為呢個 B 嘅都 B 啦，咁你個睇清楚啦。咁呢個 B 結分 B 嚟嘅，如果你唔除翻 B 嘅就咁就唔會得㗎啦。即係我哋一定要呢個 probability，所以乜都要睇。
知道 lecture 係什麼先？你今次知道？對，B 啦。我也有。對我借攞入嚟啦。係。但係呢啲多啲㗎啦。我見你。應該。
都幾好玩。你呢個時代有冇玩咩植物大意僵先？有冇玩？冇玩。係咯，好叫咩？憤怒你都冇人玩嘅。
Sorry, I think I have calculation mistake. It should be 33, not 38. We just delay by 3 minutes.你識做呢個就識做阿山，識老師就阿山文就好似老師咁嘅，我就玩一次。出面嗰啲變多層啦，你識識。快錢佢個價錢，即係如果你工程呢邊都係多唔多？即係冇咩未係就難睇。
有幾多個有數？一個我哋琴日嚟傾中嗰啲，但係佢哋未 wait list 咗一定要晒。
你補邊個？佢哋有佢都話。補邊個咧？補邊個咧？呢個佢寫一個寫唔晒。
有冇煮熟咁樣咯？
So I hope you fill in because this will be collected as a participation point and attendance point. Okay. I'll end the section at once I go over the results. So the question, can I provide? Yeah, that's what we do. Provide example. That's we're not done yet. So we'll give you example how we do it. And Bayes' theorem indeed is the most useful thing, and then it's very often used when you go to see a doctor. Okay, we will see that very soon. Oh yeah, that's happened. I also very sleepy, so you can see already a second coffee for me. So maybe a third coffee in the afternoon because very tired. Still very awake, so don't worry about that. Doesn't degrade anything about my teaching. Yeah, hopefully a good day. Oh, I don't think you can understand at the moment because I haven't even talked about that. So if you understand that, you can go. I don't think you are here because you learn it. You don't have to be here, right? You finish this. You reply, then you can just leave. I mean, if you know it already, right? So, but don't worry. You will do the assignment. And some of you told me, how can you practice? First is the quiz already. You can check it. Just do it. Second, assignment we're there either on Friday or next Monday because it depends on the other sections are going on. And why it's called PA, that same thing. It's probability A and PA. Why I do that? Because probability is easier to write in this way. I don't know, but there's usually people say it. Yeah, I want to sleep. Yeah, but I don't think this chair are very comfortable to sleep. Okay, if you go to the other lecture theater, it's more easy to sleep. I don't think this one is very comfortable to sleep. But anyway, that's why probably you are very sleepy. Yeah, if you got it right, that's good. It's rainy. Oh yeah, that can be true. Independence. Did not know Bayes' theorem the name now. Okay. Professor does not play video game. Oh. So I have to disclaimer. Probably I play video game much earlier than you guys. I play video game when I was kindergarten. And that's why I have these glasses because I play too much video game. And once I figure out that actually I have to wear glasses, almost stop playing video game. But the damage has been done. So hopefully you have to be careful about your screen time. But in the old day, because if the screens are coming from the electron, so it can hit your eye badly. But now I think this kind of LCD screen may be better. But don't spend too much time on playing games. Anyway, I'm not your dad or mom, so you decide your time is your adults. But play sensibly. Okay. Mutual exclusive and dependence are mutual. Yeah, that's true. If they're mutual exclusive, then they can't be independent. If they're independent, they cannot be mutually exclusive. Yes, that's correct. This is the case. Yes, true. Already so. Yes. Independence means actually they are not mutually exclusive, right? Mutually exclusive means the one is true, the other is not. So you know the one thing, the other will be known, right? In some cases, at least. Right? Of course, if you know one is false, you can't tell the other yet. But if you know one is true, they can tell the other. So it's just related. Yeah, tree diagram, what ratio? How to express what I learned in high school. Yeah, fancy equation. Well, you're in B school, right? You need to present everything in fancy way. Of course, in fancy ways, trying to explain this in a layman term, which is the most important part as a manager, right? You're not engineer, okay? But you're the manager, so you have to tell the story, right? If you can't tell the story, then probably ChatGPT will replace you very quickly. Okay, you have to understand what's going on, right? Otherwise, just fancy word equation is not going to make your job be there, right? You will easily get fired. But hopefully, you learn how to handle things. So I can see the speed is okay, except one person. Maybe you're very sleepy, so it's okay. But our class is record, so you can watch it again. Okay, but or I will have the same lecture in the other section, right? So you can attend that as well. If you want to learn that again, you're welcome to come to the other section to have fun again. I don't charge you for double, but as long as there's a seat there. So far it's okay. I mean, okay. So there's a joke here. During 1950s, a nuke tax in U.S. accidentally shoot a manhole cover at the rate far exceed the Earth escaping velocity. It's debate if that the manhole cover the man-made object to send to space. Blah, blah, blah. Okay, I don't. Maybe there's some joke there, but I didn't get it. But maybe have fun. If you understand, it's fun. But you don't understand, then it's still puzzling to me. But it's okay. Sleepy every day. So my recommendation is coffee every day. That's what I do when I was the first year in the college. I feel very sleepy. So every day I have a very strong coffee until the day that I figure out the coffee is no use to me. But hopefully you have some coffee. Love my glasses, thank you. Like my shirt, okay, no jokes. Not going to lie. If you like this mic, I use this mic. That's fine. I mean, I use this mic. Hopefully that you like it. Or this is joke. I don't know. Is it true or joke? So make sure that you let me know. If joke, then make it joke clear. But let me know. 1090 degree. Oh, I guess tangent is means infinity. I suppose what I meant. So sleepy. Oh, I'm sorry. I know it's going to sleepy, especially with math, but hopefully this will convince you because this is the most important rule. I would say. That's how you learn how to update. And usually, this is the part that differentiate you're a good manager or you are a normal person because you learn how to learn the information. Okay. So let's go back to this one. So let's remind you what this formula is. Is you start with your probably A, what you think about A would happen. And what we have is now you know B has been true from the evidence, then you want to update that part. Okay. And just some terminology here. Okay. People will call this one prior. Okay. Some terminology. This is called prior. Is before prior. Okay. And this called posterior is afterward. Okay. And this guy is called the likelihood. Okay. And this called the marginal. Okay. Why I talk about that? This is what you will learn if you go to medical school. They will not teach you ABC, but they will teach you in word. That's how you learn in the medical school. Okay. They will call the likelihood, prior, posterior. Okay. But I think our life is easier looking at the symbol. At least for me. I mean, I was have a hard time to do it, but there's explanation of that. I'm not going to go into detail, but the idea is we have the initial before the evidence. Okay. And take the ratio is update how update is look at how probably evidence and how likely the as a denominator, right? And the likelihood is how likely the evidence would occur under initial belief. Okay, you just update by this ratio. Okay, I will tell you why this is true. Looking at the tree diagram, I will draw some more chart to explain this formula. Okay, But this is what the terminology, if you go to medical school, if you have a friend who studied medical school, they will not do B.A.A.B. I mean, there will be something they don't understand. But they talk about this, they know. Okay. And I forget about this part. Okay. So this is a proof, as I already said. Okay. But let me first explain the language here. Okay. And I guess this is a tree diagram we know where we're already. Okay. So why I'll change our mind in this one. Okay. Now the first question is our Pyra is actually this guy. Right? Look at this, is whether A had happened or not. Okay. So this is our represent our initial thinking. Right? Now this is what we think. There's no B because B has not happened. But now we collect evidence telling you B had happened. Okay. So all you do is you do further analysis. Look at A. How likely B would happen? If without A, how likely B would happen? Okay. So is that clear? So do just remind yourself again what happened is initially you're only here. Okay. You only have the idea whether A is there or A is not there. Okay. This is what you think, right? There's nothing there. This is Pyra. Okay. And evidence tell us B has happened. Okay. You do analysis checking under A, how likely B is going to be there, B not there, right? Given A, whether B is there, not there. And look at the other case is, okay, if consider the other way around, if A is not there, how likely is B and not B? Fine? Fair. Now remember the case is now B had happened. Now B happened, okay? The sample space actually is not these 4 nodes. The sample space is only this and this because you know B had been true. Okay? The only possible case in the world under B is true is B under A and B without A. Right? We repeat. Now you know B happened. The only thing in the world that can be true is B under A and B without A. Right? This cannot be there. Right? There's no way in the world that these 2 branches were there. So the sample space shrank to this red one. Now we know it's going to be red. Then you ask, okay, how likely A had happened, right? How likely A had happened? So now the sample space shrinks, right? Because it's before it's just this guy, now it's just these 2 guys. So it's just how in these 2 possible branches, which one related to A? Only the upper one, right? So that's why the probability will be just upper guy over the sum of the 2. Right? Sum of the 2 is the sample space total, right? Just this over the sum of this. So basically, then repeat, it's just the numerator is just the first branch. The denominator will be just sum of the 2. These 2 branch. Because sum of 2 give you what? Give you the probability B, right? Right, because this add up is the total probability rule, right? B with A and B without A, right? So just like the first branch over the sum of the 2 branches there. That's the base rule. Okay, so that is the idea. Okay, so you update your belief, okay, based on your analysis here. Okay, you analyze them, you update your belief. Before you don't have anything, this is what you can do. But now you change your idea. Okay, so I agree this is still very abstract, so don't worry. I'll give you a concrete example to illustrate why this is useful and why I said this is the most useful thing probably in this class, besides regression. Is that okay? Don't worry. I'm sure that even though you say you understand, I do not believe that because it's very complicated. Okay, so let me go to this question again. Okay, you remember this question? 2 bets. Bet A have 4 white and 1 green. B has 1 white and 1 green. Okay, but the question is, I draw the ball at a bet at random, and a ball is being drawn randomly as well. So the question is, I have seen the ball is white. how likely that is A or B. Again, you ask me, hey, who going to be care about which bet or not? Okay, no sense. I don't care about this question. Remember our method. This what is capturing what? A and B are booming or recession, right? A is good economy, B is bad economy. A stock goes up, B stock, G is stock goes down, right? Y is the stock goes up, and G is the stock goes down. So what I'm doing here, this question is, suppose I know the stock market goes up, how likely that economy is going to be booming or recession, right? So we just based on stock market to learn what's going on in economy, right? You know that, I don't know whether you still remember, you learn in macroeconomics, stock market is a precursor of the economy, right? Look at stock market now, we look at the economy in the future in the 1 year later or half a year, right? So that's a very good important question, right? So look at the stock market today and then you can predict what's going on in the economy in the next half a month or next half a year or to the next year. Then you can plan your business decision, right? So this is very important, right? So once you this is the very important question, right? I hope that I convince you. So the question is the following. Let me rewrite this. This asking the probability that in given it is white, how is it going to be A, right? And given this white, how will it be, right? So to replace it, he says we saw the stock market goes up. Is it going to be good economy or bad economy? We know good economy likely to drive the stock goes up, right? So go them backward, change our mind. We often do this, right? I mean, that happened when we talk about technical analysis, right? You look at the stock price movement, how it looks like, right? The shooting star there are many shapes, right? This is going to tell you things, right? So it's the same idea here, right? And right. So if you believe in astrology, that's what we do, right? You look at the other guy or the girl, right? Ask him or her what's astrology, right? Then he tell you his pieces, or he tell you his a particular type of thing. Then you think it's Leo, right? Maybe you fit or not fit. So there's some idea there. Okay. Anyway, so let's go to see the question. So the first thing is look at if you have the white ball, you think A is more likely than B, right? Because B you have equally white and green, and B.A you have more white than green, right? Because given A, right, white is 4/5, given B is 1/2, and A and B is clearly chosen. Okay, so the question is, given this 4 pieces of information, we want to get back to this too, right? Is that clear what we're doing? Okay, don't worry, this is just a simple application. We'll give you a more detailed one there here. So as I said, you want to calculate these two guys, okay? These two guys. So how are we going to do that? Okay, just to take out your formula again, the base rule. Tell us what? The denominator is just white. Okay, the numerator will be 2 parts. One part is a prior, which is A, right? Because we want to know A given white. This is the posterior. Afterward, the initial is P of A. Okay, and what we want is the likelihood is given A was white. Okay, so the first thing to do is to calculate. You have to know the denominator, right? No matter this one the same, right? Just change to B as well. So calculate this guy denominator. Okay, you calculate first how likely the white is. White is white under A and white under B. Okay, white under A is if you draw white, how likely you have white. If you have bad B, how likely you have white, right? Because A you have half probability. One after your A, you have 4 white and 1 green, so it's 4/5. And for the B, you have 1 white and 1 green, 1 white, 1/2. Okay, so just you get is by expectation you have more white, right? So it's more than 1/2. So it's 13/20. So this is the denominator there. Okay, Once you have that, let's move on. Okay, let me clean this out. Now, once you have that, we have the denominator there. You need the numerator. Remember, the numerator is given by initially you close your eye to draw the ball, right? So that's 1/2. Okay, that's here. And under A, you have white. It's given you your knowledge about that, right? Under A, you have 5 balls, out of which 4 of them are white. So you have all the number there. You're done. Just plug in the formula, then you get there. Let me repeat, right? This is coming from the last part that you've done denominator. And this is your initial belief is 1/2. And this is from our knowledge or analysis, right? Which we know how the economy works, right? If good economy, you have 4 whites, right? If A, bad A, okay, will be there. So that's give you 8/13 will be A, and you can just do the rest is 5/13, right? But remember, you have whites either A or B, so error must be 1, just to remind you. Okay. So we have learned, okay, if this is the stock market, right? And then we learned that 8/13 is going to be good economy, right? 5/13 is a bad economy, if you like this metaphor. Okay. So far, maybe still you may not care about this because this application still looks crazy, right? But now let's give you this thing, okay? I hope people now still remember what happened 5 years ago. I think all of you are still in high school. I think that is the best of your life because you don't need to go to school, right? You're staying at home and watching the Zoom or maybe just YouTube or TikTok, but right? There's COVID. COVID is a time where it's important is people do a lot of tests. So the question like this. You know there's disease, the government know that 40% of the population is infected. Okay. And of course, if I have a medical test that actually is perfect, then I don't have this problem. But we know in science or whatever, there's some error there. Okay. For example, in this particular case, if actually you are infected, you also have positive outcome, it's 0.8. Okay. So you have disease, you still 20% go undetected. Okay. 80% you show you that you are disease. Happens, right? And also likely that if you are uninfected, okay, you also can likely have some positive result with 40%. So it's not that accurate, right? So it's a false positive, which is 40%. And this is the number, okay? So the number. So the question, of course, for a doctor, I send a guy to the lab and then he come back with the positive result. Okay. So how the doctor should think whether you are diseased or not, right? In the COVID is very important, right? So you want to see whether you send the guy to the camp, right? Right, or quarantine him for 2 weeks or so, right? So you have to know this probability, right? So this what happened is to a doctor to know whether he want to ask you to do another test or do a surgery, right? That's very important. So let us look at this question. So let's A be infected and B be positive result. Okay. So from the data, we know that 40% of the population is infected. Okay. Of course, you can change other number, but I just make it easier to type. Okay. All the thing remain unchanged. And the second one is I know given a guy who is infected, he will show positive result 0.8. Okay. And the last one is he is not infected, he still show the positive result with 0.4. So the question is, we want to do given positive result, how likely he's infected. Okay. Look, this is our prior. Without doing any test, 40% infected. Now I ask a question: is I evident from the lab saying that guy is positive test result? How likely he's infected, right? If this is high, maybe we send him to the quarantine hotel, right? Okay, that is the idea, right? So that's a thing. I mean, that happened every time when 5 years ago, right? So that's a question. It's very. I hope I convince you this is very important. Now, once with that, we go to calculation. But just to remind you how we do that is just this formula. The denominator is just B because B has happened. We're updating. This is posterior. Our prior is just A because this is what we learned. Okay, this is initially what we have. Okay, and what we do is just swap this guy, AB and B.A. Okay, so this is the formula we have. Okay, and you can see from this base formula, the first guy is here. The numerator, this guy is also there, right? So the numerator is just 0.8 times 0.4 is there already. So what's left is the denominator, right? The numerator is already there, right? So this guy, how do you do that? We will use the total probability rule. Okay, we will do it in the next slide. Okay, so just remind you that for this formula, the numerator is ready because this is a prior plus our analysis, which already we know how the accuracy of the text. Is that okay? So now look at the denominator, which is probability B. Okay, how do we do that? First, we have to know that use complement rule. If you're infected in the population, it's 0.4. You're not infected at 0.6. This is complement rule, which is nothing new. Okay. The second one is we want to calculate the denominator. We use the total probability rule. A probability B is B under A, and B without A. Right? B with A, B without A. Next, B with A can be decomposed into two parts again, which is coming from the multiplication rule. A times B under A. Okay. And under A, we know it's 0.4. And B under A is actually 0.8. Actually, this part, if you remember, this part is from the numerator. We've done that already. Okay. Okay. This is, we have done it, just done it. Okay. What is not explicit done is this guy, right? B without A. B without A can be decomposed in two parts. Probability without A and B given A is not there. So this part is already known, right? Because this is when the guy is negative, how likely he get a disease. So he showed in the test is 0.4, right? This is from the question. And this we just calculate. So give you 0.56. Okay. So you just take this as denominator and we have done in the numerator. So you can see this one. After we do all the math, okay, we just change our mind from 0.4, which is probably A. Okay. Now the guy comes back from the test result. You just change your mind to 0.57. Okay. And the question is whether you want to send him to the quarantine hotel. May or may not, but you can do this again. Okay. In this class, I only ask you to do once, right? But potentially, you can send this guy again. Okay. And Once you send this guy again, what happened to this? So this is a little bit more advanced. Now you have this number, right? This posterior become your new para, right? Because now you no longer have 0.4. This is more relevant. You would say, okay, go to test again. If you come back positive result, you do this updating, but instead of 0.4, you have 0.57 here. Just keep updating. So that means that you keep testing, you keep update, multiply by the same fraction until you are happy. That's it. So that's how learning, right? Because you just not test once, you can keep going testing, right? Your posterior become your new para. Okay, keep updating. So it can be positive, negative, but updating is like this fraction. Is that okay? So every time you just go up and go up and go up. If you're positive, if you go negative, you go down, right? Because the updating is like this, right? When positive, you go up by this, which is bigger than 1. This guy, so you go up, you're positive. Negative, you go down, right? You can do the same rule. Okay, but again, because of the introductory nature of this class, I just asked you to update once, so you don't have to update twice. But potentially, you can keep updating. So this is the idea there, right? Initially, you have 0.4. So that's the best you can do. This is the you can do, right? But now the doctor send you to the analysis, right? And this part based on historical data. This is independent of the evidence, right? But this is based on historical, how you know how good is your test, okay? And we know that actually test positive. So only relevant is these two branches, right? And we want to know how likely is A. So basically just this guy, right? Over some of this guy, 2 guy, right? So that is the idea. Okay. Suppose this is called 1, this is called 3, right? So this base rule tells us is 1 over 1 over 3, right? Maybe I use A. Maybe I call this X. Maybe call this X. This is Y. So basically base rule tell you that it's X over X plus Y, right? So that's the idea. Is that clear what we are doing? Of course, I'm sure that even though you say you are yes, probably it's not going to be fully understand. You need to do assignment to fully understand what's going on there. Okay. And here's another way. Okay. If you want to update negative, okay, how can you do that? Okay. The question is, suppose it's negative, okay, and how likely you get the disease, right? Remember before that 40% of people have disease. That means that 60% people have no disease, right? So the question is initially, right? A is 40%, okay? Now, if negative, actually drop down to a very small number, right? Half your probability, okay? So how can you calculate that? Okay? Just remember your formula, okay? This is your posterior, which is A given negative result, okay? Look at the prior. Prior is you have disease, right? This is disease under negative result, okay? And the update formula is you swap this guy, okay? And the numerator and denominator put the 1 at the back, right? So that's how I remember the formula. Okay, of course you can copy and paste. So the first thing to do is look at denominator. How can you calculate this guy? Okay. But we can already know probably B have been calculated from the previous question is 0.6, 0.56, okay, which is this here, 0.56, okay? So it's just being lazy, 1 minus, right? Because either you're B and you're not B, right? You're just being lazy or just 0.44. And if your positive result, right, and you will have 80% that you are positive, right? That's what this 0.8 is given by the question, right? 80% that if your disease, you have the disease, you get a positive result 80%. So it's very accurate. So 20% that if your disease, your negative result. So it's 0.2. Okay. So that means that you have this number, you have this number, you have this number. You calculate, you get the result. Okay, it's 20% or 18% to be precise. So of course, is it 20% is sufficient to say I can get the guy out from the quarantine hotel? Not yet, right? Probably you still think it's high risk. How are you going to do it? Test again, right? And test again means that your prior is no longer 0.4, right? You put this number in, multiply by this guy, you get lower, right? Basically by each time basically reduced by half, because look at this number. It's more like equal to 1/2. Okay. Basically each time for this test, negative, your probability of prior will reduce by half. Right? So that is this test result goes in. Okay. So if you test one more negative, then it become more like 10%. Right? And then one more negative gives you 5%. And one more negative gives you 2.5%. Right? You keep reducing half by half. Okay? So you will be when you will be enough, depends on what is the threshold. Maybe you need 5%, say. Then you have to do one negative give you 10, other negative give you, so one give you 20, one give you 10, one give you 5, you need 3 negative, consecutively negative, you can go out. All right? So this actually probably is going to be fitting our COVID, right? You need 3 negative to be go home. So this is exactly why it's going to be there. Okay? So I hope I convince you that this is very useful, right? And you can ask yourself when you will take decision, right? How long you wait until you do some action, right? This is the idea, right? Why is the wait? Because every signal you just update, right? Update until to reach the point that you want to make decision, right? Of course, whether 5%, 10%, or 1% depends on how risk preference you are, but this tells you how you update. Okay. Okay. So just repeat. Positive result will change to 56%, and negative result will keep you 18, right? So basically, if you positive result, your prior will be upgraded by 14%, right? Because 0.4 to 57 is like 40%, right? So every time you get positive result, your idea will upgrade by 40%. Okay. If your negative result, you downgrade by half. Right? So suppose you have negative result, which become 20%, right? And but again, your positive result again, you will be upgrade to 28. Right? If negative result will become 14, so on and so forth, right? So if this is upgrade positive, you go up by 40%. You downgrade is by half, right? So this is always keep the same thing. The only change is the prior and posterior, right? Once you upgrade, you change it, the new posterior become the new prior. That's how machine learn, right? Because you keep updating what you know about the world, right? And that's the question is how accurate your test depends on how fast you upgrade things, right? So if your test is very accurate, this will be very fast. This is not very fast because of the idea that you still have not very accurate. Okay? Did I convince you this is very useful? I'm not sure, but at least you find useful for exam because I ask question like this, right? So I hope that at least convince you that it's very useful. Okay. So I guess I have 2 minutes. I can talk about this last thing before I end. So this is principle counting, and that's we do often. Okay. And if I want to do something, okay, and if I do it in 2 steps, 2 tasks or 2 steps, step 1 have n1 of different way, n2 a different way. So you ask how many different way to do it, right? But you learn from your high school or even primary school, actually this is multiply this number. Why? Because you draw a 2-way table. This is first step and second step, right? The first step you have 1 up to n1 way. The second step you have 1 up to n2 way, right? And each entry in this table is one method to do it, right? So how many cells are there? You just multiply n1 over n2, right? Or for each way to do the first task, the n2 way to do it. So it's n1 times n2. Okay. In general, how many ways you can complete a task if you have k different steps? Each step is ni, just multiply. Okay. So in the example I will give is, I don't have time, but maybe do it next time. It will just how many ways you can buy food in our canteen, and we'll talk about this next time. So I'll see you on Friday, and we'll talk about this how many food you can eat in the canteen without repeating yourself. I'll see you on Friday.